This is a recap of the basics of probability. We treat cases where we deal with discrete and continuous values differently. Some examples of discrete values are natural numbers like 1, 2, 3, 4, categories like apples and pears, or one-hot vectors. Some examples of continuous values are any floating point numbers on an infinite interval, or the speed of a train. To be precise, discrete values are defined as coming from a countable set, while continuous values come from an uncountably infinite set, commonly an interval. Now we can introduce random variables and random events. A random event is an event with a non-predictable outcome, while a random variable is a variable whose value depends on the outcome of a random event. We denote random variables with uppercase letters like x, y, z. In the discrete case, we may have a random variable x, which takes the value of the outcome of a coin flip. So the value x is either h or t, depending on the outcome of the coin flip. In the continuous case, we may be measuring the height of a randomly selected person. Our random variable in this case may take values like 180.2 centimeters. Let's now introduce probability and probability distributions. First, let's take a random variable x and have it take a value based on the outcome of a coin flip. Let's say we flip the coin once and get a value heads. You can see that the single observation doesn't really tell you that much. However, observing 100 flips, we see that the heads are heavily favored, and in fact, this random coin has an 80% chance of landing on heads. So single events don't necessarily give us information, but structure can be observed in the outcomes of many different trials. We call the chance of an outcome its probability. You can think of probability as the relative frequency with which an outcome is observed. For example, 3 out of 4 times. You can also think of probability as a way to express a degree of belief in terms of a value between 0 and 1. A probability distribution is a function which maps the outcomes of random events to their probabilities. In notation, we use big P to denote a probability function which maps outcomes to real number probabilities as the output. We may write the probability that random variable x takes value little x as shown, and can use shorthand with little p of x to denote the same thing. Here little p is a probability mass function which assigns probability to outcomes in the discrete case. Given a fair coin, we may say probability of heads is 0.5. All probability values are defined such that they are between 0 and 1, and when you sum the probabilities of all possible outcomes, you get 1. In our coin flip case, assuming we can only flip heads or tails, probability of heads plus the probability of tails is 1. When working with discrete values, we saw that the sum of probabilities over all of the finite number of outcomes was 1. So what do we do in the continuous case when we have uncountably infinite set of outcomes? Suppose we assign even a small probability to every single one of the infinite outcomes. We get infinity. So it doesn't make sense in the continuous case to think about probabilities of exact outcomes. Instead, we talk about the probability of an outcome falling close to or within a range of a particular value. And when we say close, it means falling within some infinitesimal interval. We call probability in some interval a probability density. So in the continuous case, we work with probability densities, while in the discrete case, we deal with probabilities more directly, and we call that probability mass. The function which maps outcomes to densities is called a probability density function, and it must integrate to 1. There are many situations where we deal with multiple random variables. We denote the probability that x takes value little x and y takes value little y as shown. This probability is called the joint probability of x and y. Suppose we're working with a standard deck of 52 cards and the value x takes is the color of the first card drawn, while y takes as its value the color of the second card drawn from the deck without replacement. Without replacement means we do not put the first card drawn back before picking the next one. The probability that both x and y are red is a little less than 1/4. What we've just seen is a case where two random variables depend on each other. In this case, drawing a red card first means that there's one less red card to draw when the second card is taken from the deck. There are also cases where events have no influence on each other's outcomes and are said to be independent. In this case, the joint probability equals the product of the probabilities of the independent events. An example of two events with independent outcomes are rolling a fair die and flipping a fair coin. Suppose two events cannot happen at once, so their joint probability is 0. In this case, the probability of observing particular outcomes for x or y is the sum of their individual probabilities, and we call the events mutually exclusive. As an example, you cannot roll a 1 or 2 on a die, and in that same cast of the die roll a 3 or a 4. We may be interested in the probability of an event given the particular outcome of another event. For this, we use conditional probabilities. Let's look at our example of drawing two cards sequentially from the deck of cards without replacement. Let x take a value depending on the color of the first card drawn, and y take value depending on the color of the second card drawn. In this situation, we may ask what is the probability that y is red given that x is red. To help explain conditional probabilities in general, we'll use the following visualization and ignore that it implies that x and y are independent. The red box represents the number of occurrences where we observe both little x and little y as the outcome. The yellow box represents the occurrences where we have not x and not y as the outcome, where not x is 1 minus x and not y 1 minus y. So if we want to calculate the probability of x given y, we look only at the occurrences where y is observed, and out of those calculate how many times we see x as well. If we normalize counts and treat the boxes as probabilities, such that they sum to 1, in notation the red box represents the joint probability of x and y, while red and blue boxes together represent the probability of y. This is our conditional probability and it is notated as shown. If we rearrange the definition of conditional probability, we get a very useful way to re-express the joint probability. As a side note, P of y in this case can be referred to as a marginal probability in the sense that when you sum joint P of x and y over outcomes of x, you get probability of y. This process of summation is called marginalization. Bayes' theorem is a widely used and powerful way to re-express a conditional probability in terms of other probability. As you'll see, it is fairly easily derived from the definition of a conditional probability. Let's write out the definitions of the conditional probabilities of x given y and y given x. Then, as seen earlier, we will rearrange the definition of probability of y given x to show that we can express the joint probability as the probability of y given x times the probability of x. Now we substitute this expression into the definition shown on the left to give us Bayes' theorem. This is useful since we may not know probability of x given y, or it may be difficult to get its value directly. It can be much easier to simulate or get values of all the other probabilities shown on the right hand side and calculate it using Bayes' theorem. To wrap up, I want to touch on expected value and variance. An expected value of a random variable is a weighted average of its possible outcomes. The weights are the probability of the corresponding outcome. It is often denoted with capital letter E and square brackets around the random variable of interest. Variance is a measure of how spread out outcomes are from their expected value. Formally, it's defined as the expected squared difference to the expected value. Doing some rearranging of this notation and some simplification, we arrive at a useful alternate way of expressing variance.